We've talked a little bit about magnetic materials, and the reason I'm interested in it is we're actually making all kinds of interesting, mainly biomedical devices with these types of things. So let me talk a little bit of history of magnetism. You know, if you go back, it all goes back to like 600 BC, which is kind of crazy to think about. That these guys were basically walking around, checking out different things, and they found lodestone, which is basically a magnetite crystal. And because of the way it's formed geologically, it actually maintains a magnetic moment. And so these guys figured out, they called it a south pointer, is what the lodestone is. And basically they found that this rock, if you let it sit in some water, will actually float and point to the right thing. Which is kind of, a neat thing. I went and then we go in 1269, where actually it was able to map out fields. So basically we've all done this as kids, where you put the iron filings on a magnet and you can map out the field. So that was done 1269. And then Gilbert suggested the Earth is actually a permanent magnet. And we're going to talk in a second about the Earth's magnetic field, and that's actually very fascinating. Ørsted actually found the relationship between electricity and magnetism. And then we'll take that, we'll find that Ørsted is a common unit that we use. And then another unit we commonly use is amperes, or amps, you guys know well. Actually using the magnetic force, and we'll talk more about that in a second, using Ampere's law. And then we have Henry and Faraday. We're actually looking at induction and how magnetic fields and electricity, and you guys probably know that very well. I always laugh at people who don't understand induction. What's the best example of induction that you guys can think of? Is that induction, or is that?
I don't know.
That's like static electricity formation. I think of induction, I always think about the little sensors that have on the stoplights. It's basically a coil that they're actually measuring the change of inductions as a car drives over it. So I was out biking yesterday, and I was sitting at this light. I'm like, crap, my bike does not have enough metal in it to actually trigger the sensor. But a big heavy car that's full of steel will actually go over the coil, change the current, or the cause a change in current and voltage, and that's because of that magnetic field, the very slight magnetic field that coil is generating. So I always laugh, people like try and stomp on those things. They think it's like weight induced. Yeah, it's kind of silly. That'd be a big pain to build a big scale at every stoplight. Anyway, so Maxwell equations show that the reverse happens too, which is kind of neat. All right, so we're sitting on a big giant magnet, the Earth's magnetic field. It's about 60 Ørsteds, if I remember correctly, or milliOrsteds. And basically it goes through slightly off to actually the true geographic north. So if you think about where the Earth's spinning on its axis, the Earth's magnetic field is actually canted over slightly a bit. That is not permanent. Every few thousand years, the Earth's magnetic field actually switches. So the north becomes south, and south becomes north. We're actually due. As in due as in like the next, we've been due for about the last 100 years or so, if not more. So someday, maybe we'll wake up tomorrow, and the Earth's magnetic field will have switched, which I think is kind of fascinating to think about. You can actually see this geologically, and how different rocks are formed, and actually they switch depending on when, what the Earth's magnetic field's actually oriented, which I think is kind of crazy to think about. So think about all the things that rely on the Earth's magnetic field. A lot of our GPS systems, their coordination does, cars, transportation, everything relies on the Earth's magnetic field. And if we wake up tomorrow and it's switched, that could have very interesting effects. One of the reasons your phone actually can orient itself is actually it's looking for the Earth's magnetic field. That's actually how Google Maps knows. There's actually a little magnetometer in your phone. You can buy a free app, or well, I guess it's not buying, but you can get a free app that actually you can detect magnetic fields with your phone. It's actually kind of cool. It's not the most sensitive one because the chip's really, really small, but you can actually see the Earth's magnetic field actually as you walk around, and you can see stray fields from various other things. I think it's just kind of a fascinating thing. So we've talked about this, and so let's talk about like what creates a magnetic field. So as electrical engineers, we basically are putting current through a wire, and everyone use their right-hand rule. I love going to like freshman physics class when they're doing an exam because you see all these students like, and then the student who's not doing very well does this. So you have a little bit of that. So we've basically got our current going through a wire. We can use our right-hand rule, and we actually can see that, okay, we can actually generate our B field. So you can see here, given a certain current, and that comes from the electron rotation. We can take a little bit further look at that, where we're actually looking at both Ampere's law. So this is basically that B field is generated from the current, and we're going to multiply that by the permeability of free space times 2 pi r. We're actually defining this. And so that permeability of free space is basically a constant 4 pi times 10 to the negative 7th Tesla per meter per ampere. And we'll talk about units in a second. We can also use Biot-Savart. I've been told the T is silent here, like Colbert. And basically we're looking at what is the field induced from a certain thing. So the nice thing is we actually have pretty good things. And what we can do is actually take these models, and rather than doing a single wire, we can actually look at something like a solenoid. And a solenoid is kind of a classic magnetic field generation where we have a bunch of wires, and here wires are coming in and out to actually make our solenoid. And we actually can calculate that B field, the magnetic field generated, as the permeability free space times the number of turns times the current in amperes, and this is in length. So let's talk about units for a second. What's the field going to come out at? Now let's back up for a second. Wish I had a whiteboard. So we know that permeability free space is in Tesla meters per amp, right? And we're going to multiply that by amps, so the amps cancel out. Number of turns, what's the units for number of turns? Nothing, no turns there. And then length, meters. So we're actually that results in Tesla. You can also do the same type calculation, and rather than putting it in Tesla, you can actually get another unit in amps per meter. So not including the permeability free space or using a different term for it. You can also get terms of either Tesla or amps per meter. So where's all this magnetic field coming from? So the classical view, and I'll speak in classical views, there's also a quantum explanation, but we don't have time for that this morning. We're basically looking at the spin states of these electrons. And so all we're interested in is what's actually going on with the electrons. So you can see, basically looking at the property of these spin states, we actually can have either spin up or spin down. And so it depends on what's going on then. And so when we look at solid materials, or like solid state materials, we actually can look at that magnetization based on those electron structures. So one can imagine, like here in a bar magnet, for example, this is just a very basic example. We're basically looking at the spin state of the electrons in that solid material. And so basically what's actually going on with those electrons. And so we can actually put this as, what is the magnetization per volume, and we're going to call that magnetization. So magnetic moment per volume is going to be magnetization. So there's two big terms, magnetization and field. Now that field, we can describe a couple different ways. That field strength is basically, we're actually looking at how a material is actually magnetized. And this basically, we can look at the effect, basically if we take our magnet and actually put it into a solenoid, we actually can look at the effect it has on there. We also can look at what is actually what it would be if we actually had it in a wire structure. So here we have our effective B field over our permeability, free space. That's going to give us our H field. So there's two types of magnetic fields. There's the H field and the B field. And so where do these derive from? So the B field, we have our free space field and our magnetic mobilization field. And so if we can combine these, we actually get into this term here. And this, the way I always think about this is this B field's coming from two different things. We have our permeability free space, and then we have our magnetization of basically a vacuum. So if there's nothing there, what would our field be? And then we actually have this induced field. This is actually from the magnetization of the material in there. So even if we've got a solenoid full of air, we have to actually account for the magnetization of the air molecules in there. So how magnetic is air?
Not very.
Not very. Now, absolute vacuum would be a lot better. but we do need to account for that a little bit. So that's where this B field and H field. So, if you have something that has a very low magnetization, you can actually reduce this term, and so now B becomes equivalent to the permeability free space times that H field. And so that's understanding the magnetization of the material plays into that. So the worst part about magnetics, in my mind, are the units. So there are 3 systems of units. So normally, like most scientific fields, you have your, Anglo system, and you have your SI. So we've got SI, the Anglo-derived system, and then the CGS system. So there's actually 3 different systems all used. And so either you're mostly dealing with SI, which is meters, seconds, kilograms, and amps, which I like to work with. And then there's this crazy group. I don't know who to blame. I don't know to blame the physicists. I'll blame you. Or blame the electrical engineers. I'll blame them as well. They like working these crazy units of centimeters, grams, and seconds per coulomb. Why use these units, I don't know, but people really like it. So you can see, like, even force, we're dealing with something like crazy things like Dians and Maxwell's, Gauss, Ørsted's, EMUs, which is basically electromagnetic unit. To me, like amps meter squared just makes more mental sense. So maybe that's my pure physics training. You all have debate on this? What units did you prefer to work in? Think about that. So, and then we can look at basically doing conversions from all these. So that's the nice thing is traditionally the field, I would say, if you read papers, a lot of people primarily use the CGS system. In the last 5 to 10 years, I'd say, you're seeing a lot more shift to people primarily using everything in SI. I think that's coming a lot from our national agencies. I know anytime NIST people write a paper, it has to be only in SI units, which is a pain sometimes. Then and I think the NIH may be implementing that a little bit more too. So let's look at characterization. How do we measure a magnetic field? So what would be the easiest way to measure a magnetic field? Any guesses, thoughts?
Force that exerts on something.
Okay, force that exerts on something. So, a good example would be a compass, right? If you think, so why does the compass point north?
It's aligning with the Earth's magnetic.
Right. So let's think of the case where the worst possible case here. Well, not the worst possible. A case where the compass, you pick it out of your pocket, you shake it up. Compass needle happens to be 90 degrees to the Earth's magnetic field. So you got your compass needle going this way, Earth's magnetic field's going this way. What's going to happen? It's going to shift, right? So what causes that change? What causes why does the compass needle move? The compass needle has a magnetic moment. The Earth's field has a magnetic field, obviously. So what causes it actually to move? So one way to think about it is actually it's applying a torque to that compass needle. And that torque is actually what causes the force to actually cause it to align. And so think about that. That's actually pretty remarkable. And then you actually end up with some dampening actually occurring. So actually, ideally, they actually would overshoot because of the force. And they actually have some dampening causes that actually cause the compass to finally align with the Earth's magnetic field. So actually, a compass being a very simple instrument is actually fairly remarkable that the physics and actually how it works. So that torque effect is something very important. So that's one way to measure a magnetic field. How else could we measure a magnetic field? So we talked about induction earlier, right, where we have our current going through a coil, and we actually measure the change in that resistance as the object enters that field and changes the induction of that magnetic field. Could we do the reverse? All right? So say we applied a magnetic field to just one coil, what will happen? Yeah, we can induce a current. So that's a very, very, what we would call that a search coil. Very simple coil where we actually can measure that current. And so you guys are good electrical engineers. What's the easiest thing to measure?
Voltage.
Voltage, yeah. Or actually probably a better way of putting it, at least correct me if I'm wrong, Rod, please jump in here. Change in voltage is actually easier to measure than voltage itself.
Probably.
Yeah, so measuring small change. So that's the interesting thing, is actually measuring that change is actually a very effective way. So now we've got compass, which you can tell us direction. Now we've got actually an amplitude by measuring the change in voltage. And so we've got some different ways to actually measure these different fields. And so if you think about it, these are actually fairly simple. So let's talk about different types of magnets now, since we're kind of running short on time. I'll try and be brief here. Permanent magnet. So what's an example of a permanent magnet? Okay, like the lodestone we talked about. I always think about like fridge magnets. The coercivity and actually retentive magnetic properties, looking at saturation, so we actually can look at our full hysteresis loop. We can also look at anti-ferromagnetic materials, where we're actually looking at materials, actually they're very temperature dependent on their susceptibility. And actually what you'll see is the susceptibility will change depending on that. And what you have is actually this Néel temperature that actually occurs where the magnetic moments, or the susceptibility magnetic moments, actually plateaus and then actually enters a paramagnetic regime. So this kind of gives you an idea. And then the final thing, then this is where my group actually spends most of its time, is we've talked about multi-domain particles. What we do is we actually make magnetic nanoparticles. And the size of the particles range from about 5 nanometers all the way to about 25 nanometers depending on the material. And what happens is, because we've actually gotten the material so small that the domain walls energetically can't form. And so we actually end up with what's called monodomain materials. So these actually, each little nanoparticle is what we call magnetically hard, meaning that there is no domain walls within it, and so therefore it maintains one single dipole within that structure. And so size is actually very critical for making this happen. We also have multi-domain particles. This is actually, you get a little bit bigger. The change in magnetization is much easier to accomplish when you happen. But one of the effects of having these monodomain particles is actually a unique behavior called superparamagnetism. So you can look at this, is actually the superparamagnetism is actually very size dependent. So we talked about, we have this superparamagnetic regime, and there's a critical size for that. You have to be below a certain size for that to actually occur. And we can look at single domain particles, where actually look at that critical size where the coercivity actually is at its maximum. And then we can go to multi-domain where that coercivity actually drops off. And so by changing particle size or grain size, maybe a good way to think about it for some applications, we actually can change the coercivity of that material. And I think, to me, coming back from my chemistry background, I think that's really powerful. Is that by changing fundamentally the properties of that material, we can change the magnetic properties. And I think that's a kind of a fun game that synthetically I'm challenged by. Is, okay, how can we actually improve upon this and actually improve the properties of these materials? So we'll skip that. I'll skip that. One final thing is to actually talk about remnant magnetization. Talk about remnant magnetization. We're actually looking at the remaining magnetic field. And this goes back to how your hard drive works.